Things are going okay. We got a quiz on Thursday over 2-3 and 2-4 homework. That will probably just be 2 problems, since you'll actually have to do more solving on those. So probably be 1 out of 2-3 and 1 out of 2-4. I say probably because I haven't actually written it yet, but that's my thought. So just to give you an idea of what I'm thinking for that particular quiz.
Is it just over the practice problems that you have us write down?
Yeah. Yep. Right off of those. Yeah. Yep. What's that?
Live integration by parts.
Yeah, absolutely. You should be able to do an integration by parts at least 5 times on it.
That's super exciting.
That seems a little unnecessary. All right.
X to the 5th.
Yeah, X to the 5th. And then they get like a sign of 9x or something just to get that coefficient in there to go along with it. Just to keep it, keep you on your toes. Why is that so? I need to adjust the screen. Seems to be getting worse. Okay. The screen in 318 was just stay down yesterday, so it's all right. Again, to remind, we've got our second math candidate on campus tomorrow. So if you're able to come at 2, great for the research presentation. You already have that information, but yeah, it's a long week for me with candidates on campus. Get to go to dinner again tonight. It's all sorts of fun. All right. So we've talked about linear equations and we started exact equations. We're going to finish that up today. We're going to talk about a couple of other methods to solve first order equations today as well. A couple of special methods. And then maybe by the end of class, but definitely on Thursday, we will have our first numeric approximation method for solving differential equations. Okay, so that's where we're headed. So let's go back to exact again. For exact equations, just to remind, the format looks like this, where you've got some fun. I've suppressed the of x, y. M and n are functions of x and y. So you've got m with the dx and the n with the dy equals 0. So again, we think of this left-hand side as hopefully a total differential of some function of f of x, y. If that is going to be the total differential of some function, then how does the function m relate to f? How does it? What is m as it relates to f?
The partial of y.
It's the partial with respect to x, right? It's on the dx piece.
Oh,
yeah. And so n is the partial with respect to y. Now, if this is going to be exact, then we have our check, right? And that's where the next part's coming in. Yeah. So if it's going to be exact, how do we check? What has to be true about m and n if you go to a second derivative? Yeah, what should be the same? You're right. There should be some part of being the same, but
derivative with y.
yeah. So when we do the second derivatives, right? These are first derivatives. The m and the n are some first derivatives. When we do a mixed second partial, those have to be the same, right? So if m is the derivative of f with respect to x, I'm going to differentiate that with respect to y. Likewise, if n is the derivative with respect to y, I'm going to differentiate that with respect to x, and they better agree. It's going to be an exact equation, right? So if it's exact, if this equation is exact, we need the partial of m with respect to y to equal the partial of n with respect to x. We need those mixed second partials to agree. So that's the first thing we have to do. Is if we're going to have an exact equation, we have to check that actually works. All right. So let's remind ourselves with a kind of a straightforward problem. Let's look at number 10 in this section. I think we did number 4 last time, right? I think it was the only one we did. Yeah. Okay. Let's look at number 10. We've got x cubed plus y cubed dx plus 3x squared. Sorry, try that again. 3xy squared dy equals 0. All right. So again, we're hoping that left-hand side is the total differential of some function. So that x cubed plus y cubed needs to be the derivative with respect to x, and the 3xy squared needs to be the derivative with respect to y, right? So if we're going to check to see that it's exact, we're going to take our derivative with respect to y, this is a partial, of the x cubed plus y cubed. When we take the derivative with respect to y, what do we get?
X cubed plus y squared. Oh wait, there's a plus there.
There's a plus, yeah.
0 plus 3y squared.
Good, yep. This is the 3y squared, right? Because the x cubed is a constant. Derivative of the constant is just 0. Go the other way. Partial with respect to x of the 3xy squared. It's also 3y squared. Good. So these are equal. So it is exact. All right. So again, since it's exact, this part must be the partial of some function with respect to x. That's the idea, right? Since it is exact, that first function should be the partial with respect to x for some function. Well, if I differentiate with respect to x and get that answer, what should I do to go back to the original function? Integrate. Good. Yeah, we'll integrate with respect to x. So we'll take the integral of x cubed plus y cubed dx. Remember, again, we're treating the y as a constant here, right? Antiderivative for x cubed will be good. And antiderivative of y cubed with respect to x is what? Xy cubed. Good. Now, we're doing an indefinite integral because I don't know what the function is. I don't have an initial condition. But instead of having an arbitrary constant, remember, if I start with my function and I differentiate with respect to x, anything that has no x's in it, we treat as a constant. So if I differentiate anything with a y all by itself, I would get 0, right? So rather than writing an arbitrary constant here, we're going to write an arbitrary function of y. Typically, we choose a g. Doesn't really matter what the letter is as long as it's not a letter you've used. Okay? Pick whatever letter you want. Or symbol, I don't care. Use a Greek letter. Use an emoji. Use a picture of Devil's Tower out in Wyoming. I don't really care. Okay? As long as it's something you haven't used before. Okay? It just needs to be something to represent the function. All right. So this isn't quite done because I'm okay with an arbitrary constant. I'm not okay with an arbitrary function of a variable. Okay? I need to figure out what this is. Okay? That's the next step. Okay. So now again, going back up here, we know that this piece here should be the derivative of whatever my function f is with respect to y. What that means is that when we differentiate this piece right here, I should get this piece right here. Okay? So if we take the partial with respect to y of the 1/4 x to the 4th plus xy cubed plus whatever this arbitrary function of y is, we should get 3xy squared. That's what we should get when we're done. Let's look at the left-hand side. Differentiate with respect to y. What happens to this? First term, it goes away, right? So we'll get a 0 here for this one. 3xy squared, good. This part, careful. Yeah, it's just a g prime, right? I don't know what it is, so I'm going to call it g prime. That's the issue, right? I need to figure out what g is. Okay. Now notice on the right-hand side, we're not differentiating, right? We want the derivative of what we came up with in the first step to equal what that n function is. Does that make sense? Okay. It's not like other things where you differentiate both sides or integrate both sides, right? We take the derivative, we want to equal this thing. Now, this is if your equation is exact, this should happen every single time. If there's an x on the left-hand side, it better match up with something on the right-hand side with the same x in it, because any x's need to go away. Okay? The reason for that is we're left with the derivative of a function in only y. It can't have any x's in it. Okay? If at this step you've got an x left, after you simplify, you've done something incorrectly, go back and fix it. If it's truly exact. Okay. All right. Notice in this case it does, right? This cancels with that. And we just get g prime of y equals 0. Well, if the derivative of the function turned out to be 0, what did the function have to be to start with? Constant, yeah. So this is just, it does turn out just to be an arbitrary constant. So then our f of x, y, is 1/4 x to the 4th plus xy cubed plus a constant. Now, that's not the answer, okay? That's the function that we found, right? We said that, pardon me, we said that the original equation looked like this here, right? That was our original equation. Okay. Notice on the right-hand side, we have a 0, correct? So when we write our final answer actually just becomes 1/4 x to the 4th plus xy cubed equals a constant. Because when I take the derivative of both sides, I would get a 0 on the right-hand side. When I do the total differential, I would get a 0. Okay. So this would be your answer. You could solve for y in this case. In general, you're going to get a relation that involves x and y, and you won't be able to solve for y exactly. So you can just leave it like this. However, I will mention, since we've mentioned this a couple of times, if you try to solve for y, I would need to divide by an x, right? If I divide by an x, I introduce a discontinuity, so you should know that your solution is either going to be valid 0 to infinity or negative infinity to 0 if you've got an initial condition. I shouldn't say valid, unique is what I should say. This one okay? This is the process every time. You could do an analogous process just the other way. Notice we integrated with respect to x here, and then differentiated with respect to y here. You could do the reverse. I could integrate with respect to y and differentiate with respect to x. You'll get the same answer. Literally doesn't matter. The only reason that you might want to do one over the other is if it's easier to integrate one versus the other. You might want to do it the other way. But in general, if you do it this way every single time, it'll work every single time. Again, as long as the equation is exact to start with. All right, let's do another one. Let's do number 6. Number 6 has written this way, 2y minus 1 over x plus cosine 3x, and then dy dx, and then plus y over x squared minus 4x cubed plus 3y sine of 3x equals 0. It's a long thing. We don't have a lot of tools yet to solve the equations that we come up with. This one actually is linear in y. So it is first order linear, so you could actually attack. Oh, no, it's not. Never mind. I lied. Why is this not linear in y? Sorry. I got tricked. I don't have a problem here or here, do I? But it's not linear in y because that y is multiplied by that dy dx, and I'm not allowed to do that for a linear one. So be careful with that. I actually got tricked, didn't I? Okay? This is not first order linear. Okay? Probably going to have a hard time separating things. Notice here, this is not attached to a dy dx at all, and I'm not going to be able to factor a y out of every single term. And I have the same issue over here. So this is probably not separable. So the only other hammer you have currently is exact. Okay. So if it's going to be an exact equation, again, remember, we need it to be in this form to start with, right? The equation they gave us is not in that form. We need to rearrange it, right? So I need to put it looks like I'm going to multiply by dx. That's not really what we're doing. We're just putting it in a differential form, right? I need to put this dx with this piece, right? And then I'll reverse the order just so it looks like that form that we had originally, okay? So we'll write this as y over x squared minus 4, that's a y, over 4x cubed, minus 4x cubed, plus 3y sine of 3x dx, plus 2y minus 1 over x plus cosine 3x dy equals 0. I'm only writing it this way, again, to put it in that form that we saw for exact when we started all this discussion to begin with. Okay. Now, again, we do our check. If it's not exact, well, currently would be screwed because we don't know how to attack it. We'll talk about a way we can possibly attack it if it's not exact here in a little bit. Okay. So this better be exact, or we just say it's not exact and go on with life. Okay. So in order for it to be exact, we need to identify our pieces. This again here would be your M. This part here would be your N. I need to take the partial of M with respect to Y and hope it's the same thing as the partial of N with respect to X. What is the partial of M with respect to Y? What do we get? Good. Everybody okay with the derivatives? Now would be the time to ask if you're not okay with the derivatives. Okay. With respect to X, what do we get? They weren't very nice twos.
Minus 3 sine.
Okay. Just double checking, make sure I wrote down the problem right. Is this exact then? No, they're not equal, right? This and this aren't the same. Okay, so this is not exact. And like I said, we'd be screwed at this point. Okay, Well, there is going to be a way that we can attack this in some instances. We can't always attack it. Okay. So just to make the problem doable for us right now, let's just make a small adjustment because I'd actually like to go through and solve the problem. Okay. So in order to do that, let's just change this plus sign to a minus right here. So let's make it a minus cosine 3x. And then that'll change this to a plus 3 sine 3x. And so then it is exact at that point. I know I cheated a little bit. Okay. But I want to actually be able to solve it. Okay. Moral of the story is make sure that you actually take your derivatives and check it. If it's not exact, you're going to run into a problem at that step where you're trying to solve for the g prime of y. That's when you'll discover it. All right. So again, first step is to do what? Yeah, integrate. We'll integrate the m. You want to integrate the m with respect to x or with respect to y? There's a hint. It has a dx on it. Yeah, it's better the x because it's got the dx on it, right? That's the thing we would have differentiated with respect to x, right? So, what's that? I don't think either of them are that hard. Do you want to do the other one? Okay. Trey says we're going to do the other one first. All right, let's integrate this with respect to y. What didn't you like about the other one? It's true. I don't have to. You're right. I don't have to integrate a trig function. At least it wasn't by parts. It was just literally the trig function. Okay. All right. Integrate with respect to y. Okay. This is actually it's a good thought. You don't have to do either of them. Right? I mean, there's not one that you have to do over the other. You can do either one you want. Antiderivative of 2y. Good. Antiderivative of 1 over x with respect to y. Good. Antiderivative of cosine of 3x with respect to y. Good. Exactly right. So Trace is right. That was an easier integral. Right? That was pretty easy. The two pieces are constants. Now, what goes on the end? A g of x. Good. It's some arbitrary function of x. Good. Some arbitrary function of x with no y. All right. What do you think we should do next? Good. Exactly right. So we integrated this part. So we're going to differentiate now to get this part. Okay. So we'll do our partial with respect to x of the thing we just found better equal this other mess. Oops, squared. Oops. I forgot a piece, didn't I? I forgot my g of x in here. All right, what do you get when you take the partial with respect to x on the left-hand side? The y squared goes away, good. Yeah, it better be a plus y over x squared. Why do I know it better be a plus y over x squared? Yeah, so looking at my two sides, remember when I'm done, what's left has to be a function of x all by itself, right? This better cancel. This also better cancel, right? I better see this and I better see this in my derivative. Because those have to go away. Anything that's left has to be a function of x all by itself in this case, right? I cannot have a mix of variables at this stage. If I did, it wasn't exact to start with, right? All right, so that was why I knew it had to be a positive y over x squared, because it's got to cancel with the other one on the other side. Derivative of the negative y cosine 3x, again, better be positive 3y sine of 3x, and it is, right? And then plus g prime of x. So again, the y over x squareds go away, the 3y sine 3x's go away, and we're left with g prime of x equals negative 4x cubed. If the derivative was negative 4x cubed, what did the original function need to be? Yeah, negative x to the fourth. So now we're just about ready to write our answer. Our function, remember again, this was our function that we came up with in the first step, right? Okay. So our function is y squared minus y over x minus y cosine 3x minus x to the fourth. And on the right-hand side, we'll have a c. That'll be our solution. I don't need to worry about putting the plus c in the antiderivative at the end, because we're going to incorporate it in our answer when we set the function equal to the constant. It'll get incorporated there.
You're always going to put a c there.
There's always, well, yes, because our original equation was this thing. Oops, no, this thing.
Can it be exact if it's not equal to 0?
Yeah, you could. Oh, no, actually I can't, because we're setting total differential equal to 0. Yeah. Because it's the total differential, not a function of a single variable. So it needs to have a 0 there. Basically, what you're doing is looking at where a tangent plane would be horizontal, kind of idea. Since you've got that thing equal to 0, then you must be looking at some sort of a kind of a tangent plane idea. Right. This one okay? All right, let's see if we can do one that has an initial condition. And then we'll talk about how what one plan of attack would be if it's not exact. Okay? So let's look at number 20. Oops, that's not the pen. Number 24. I still had the laser pointer thing on there. 24, 3y squared minus t squared, oops, that's a t, over y to the fifth, dy dt plus t over 2y to the fourth equals 0. That was the first Tuesday of the month. All right, so again, let's think about the tools that you know and see why you might think of this as exact versus the other ones. Let's do linear first, because that's easier. Is this linear in either of the variables? No, that's pretty easy, right? There's a t squared, there's a y squared. I'm done. It's not linear, right? The other hammer that we have is separable. This is probably not separable because of that minus sign, right? If we're going to be able to separate, we have to be able to factor as multiplication of two functions. If we're going to be able to factor, I need to have y's times t's, not y's plus t's. Right? So if it's neither of those two things, it better be exact. Otherwise, we're kind of stuck. Okay? All right. To write this in the correct form, let's just move the dt to the other term. Okay? The order really doesn't matter. Usually you do, I'm going to write it this way to start with. Usually you'll do independent variable first and dependent variable second if you think of one as being independent versus dependent. But again, we're looking for a function of x and y, or in this case of t and y. Both of those variables would be independent. It really doesn't matter. The order really doesn't matter. Usually we think of y as a function of t, especially when we've got dy dt written that way. So you might write the dt and then the dy, but practically it makes zero difference. Okay? All right. So first thing we need to do is check that it really is exact. What do we need to differentiate this part with respect to? T, and this one with respect to y, right? Okay. So let's do that. We'll take the partial with respect to t of the 3y squared minus t squared over y to the fifth. And we'll take the partial with respect to y of t. Hello. That was bizarre. Why is my pen not working? Sorry. We're experiencing technical difficulties. Please stand by. What? There we go. I don't know what it was doing. All right, y equals, or not equals, of the t over 2y to the fourth. Okay. All right. Derivative with respect to t for the first part. Good. Negative 2t over y to the fifth. The first part is just a constant, isn't it? The 3y squared is just a constant with respect to t. Derivative of that is just a 0. Derivative of the t squared is 2t, and the minus sign and the y to the fifth are just constants, so they just get tagged on. Okay. On the bottom, what's your derivative? You go the other way, right? Yeah. I write that as y to the minus 4. I don't think it's an 8. I do get it as a y to the fifth, and there's a t. So this is t over 2 times y to the negative fourth. What do you get when you bring the negative 4 down? It's a negative 2, isn't it? 4 times a half. Better be if it's going to be exact, right? Otherwise, it's a really bad. Oh, I forgot to give you the initial condition. We'll do that in a minute. The whole reason I do this was to handle the initial condition. All right. So it is exact. That was the important part. Okay. What do we do first then? Yeah, we need to integrate one and differentiate back, right? Which one do you want to integrate? Okay, we'll do the dt. Sure, that's fine. Literally does not matter as long as you integrate one of them, right? Okay. Antiderivative of t over 2y to the fourth dt. What do we get?
T squared over 4y.
Okay. Okay. Antiderivative of t is 1/2 t squared. And the other pieces are just constants, right? Now what do we do? We integrated with respect to t, so now we want to differentiate with respect to y. Yeah, do the other one, right? We're going to integrate with respect to one, differentiate with respect to the other every single time, right? So we want the partial of the thing we just came up with respect to y better equal what? The dy piece, which was 3y squared minus t squared over y to the fifth. What absolutely has to go away at this step? Even before we simplify anything, what do you know has to go away? Yeah, the t's have to go away, right? This is going to have to go away. Has to go away because we're going to integrate with respect to y at the end, right? That piece has to go away. All right. Derivative with respect to y. I'm going to do the easy one. Plus g prime of y. You tell me the other one. Good. It's a y to the negative 4 again, right? Its derivative is negative 4y to the negative 5. The 4's will cancel. To help us out a little bit, let's split that fraction. I can write it as 3y squared over y to the fifth. That simplifies to 3 over y cubed minus t squared over y to the fifth. Does the piece that needs to go away go away? Yes, good. The piece that needs to go away goes away. To help out a little bit, let me write it as 3y to the negative 3. We need an antiderivative. What do we get for an antiderivative?
Negative 3 over 2y.
Good. So if we want to write our general solution, then what does our general solution look like? Good. Equals C. Good. Wonderful.
Is it t squared over 4y?
It is. I just didn't write it. Thank you. Val even said t squared. I just literally didn't write it. Good. All right. The part of this problem that I wanted to do, the reason why I did this problem is it had an initial condition. Y of 1 equals 1. Not the best example of an initial condition, but let's remind ourselves which of the ones refers to the t. The first one or the second one? Which one's the t? The first one, the one that's on the inside, right? Y of t equals something, right? So the first one is the t. The second one is the y, right? So we'll plug it into the different spots. 1 squared over 4 times 1 to the fourth, that's a minus. 3 over 2 times 1 squared equals a constant. It's pretty easy. We just need to simplify the arithmetic. 12 over 4 is 4, which is 8 halves. Excuse me, try that again. 12 over 4 is 3, which is 6 halves, minus 3 halves is just a 3 halves. You're right. Thank you. God. I should just stop. 1 squared over 4. Okay. How about that again? 1/4 minus 6/4 is negative 5/4. Is that better? Okay. Thank you. 1 squared out of 12. You know what you're supposed to do when I make a mistake that bad? You're supposed to boo me. Boo! All right. I expect it next time. If we make a mistake like that, you need to boo. Okay. Counting on all of you. All right. So then your final solution then is t squared over 4y to the 4th minus 3 over 2y squared equals negative 5/4. That would be your final answer in this one. Assuming that you can do arithmetic, putting in the initial condition shouldn't be bad, right? We've got the function equals constant. You literally just plug the initial condition into the function, and that gives you the constant. So that final step shouldn't be that bad, hopefully, unless you're an idiot like me. Yes, Trace.
That's an explicit solution?
It is not an explicit solution. That's an implicit solution. Implicit. Yeah. This was implicit because we did not explicitly solve it for y. It's not y. It's not in the form of y equals something in terms of just t.
Oh, okay.
Yeah.
So if you solve for y, right?
Yeah, go right ahead. Yes, if you do, that's correct. This would be difficult to do. The first thing you would need to do is if this is quadratic and 1 over y squared, so you'd have to use the quadratic formula because it's not going to factor. And then you've got to pick out the correct solution of the plus or minus piece that satisfies this. And then you've got a y squared, so you have to do it again.
I'm good.
Yeah, I figured you would be good. Yes. I would not suggest going through and doing the explicit solution here, but you can. This one you can actually do. You just have to make 2 choices along the way and use the quadratic formula.
If you did t as a function of y, is that explicit still, or is that?
If you did t as a function of y, that would be an explicit solution, but not for the problem we were given. The reason for that is we were said to find dy dt, so we're treating y as a function of t. You'd have to convert your problem the other way around. Other questions? That's a good question. Yeah, this is an implicit solution. Yeah, because we did not solve for the y, and I wouldn't suggest doing it. If you really wanted to use a computer, there's computer algebra systems that can solve it quick for you. I would not do that by hand. All right. Nothing else? What's that?
Extra credit problem.
No, not that particular one. No. But that's a good question. I could always do that in the future. I tell you what would be extra credit for something like this. There's a Python package called SciPy, which does things explicitly. If you can figure out how to do it on there and turn that in, I would accept that for extra credit. All right. Let's do one more where we start with something that is not exact, but need to convert it to exact. Okay? Sound like fun? Sure, why not? Let's look at number 36. All right. So 36 says cosine x dx plus 1 plus 2 over y sine of x dy equals 0. Pardon me. All right. So if we were to check whether or not it's exact, we want to take our partial with respect to y of cosine x and our partial with respect to x of 1 plus 2 over y sine x. Right? Those are the 2 pieces we would need to do. First part is 0. Yeah. The second part is, it's 1 plus 2 over y cosine x. Right? Those are definitely not equal. So this is not exact. All right. All right. So what I mentioned before was at this point we'd be kind of screwed, right? We couldn't be able to do anything. Okay. But there is a thing that we can do in certain circumstances. Remember when we did first order linear differential equations, we found an integrating factor, right? To be able to help us rewrite the left-hand side as a product rule and be able to work backwards, right? Same concept here. We're going to try to find something to multiply both sides by so that we can actually integrate and get what we want back to that original function. Okay? So here's how that works. Let's do it generally and then talk about how you do it in practice. All right, so we start with m dx plus n dy equals 0. And I want to multiply both sides by some integrating factor. Your book refers to the integrating factor as a mu, so I'll use a mu. Mathematicians love Greek letters. Okay. So let's multiply both sides by mu. All right. The goal, of course, is not to just multiply by some random function. I want a function that makes this exact, right? I now want my partial pieces to match, correct? We want mu so that when I take the partial of mu times m with respect to y, we need that to equal the partial with respect to x of mu times n. We want it to be exact. That's the condition for being exact, right? I don't want to just multiply by random things and see if it works. I want a specific function that will do the job. Okay? All right, so let's start simplifying this a little bit. This is a product of two functions, so I'd have to use the product rule. Mu y times m plus mu times my. Same thing on the right-hand side, just with x's and n's. Now let's gather some things. Let's gather things that have just mu's by themselves. So on the left-hand side, I can write this as mu times m sub y minus n sub x. And on the right-hand side, we would have mu sub x and minus mu sub y m. That doesn't look like it helped, does it? No. But what we would like is that our function mu really only has one variable rather than two. If it only has one variable, then one of those is a 0, right? Okay. So let's say that it doesn't have any y's in it. Just for argument's sake, it might also have no x's, but let's say it has no y's. Okay? If it has no y's, then this piece goes away, right? We agree? So then we can actually solve this for mu sub x. Does that look like a differential equation we can solve? Assuming we only have x's. Does that look like a differential equation we can solve? Yeah, this looks like an e to the x, doesn't it? The derivative is a multiple of the original function. Right? Okay. So what we need is this piece. When we do this computation, it better not have any x's in it. That's the special case. Okay? If this, when I do this computation, when I take the partial of m with respect to y, subtract the partial of n with respect to x, and divide by n, it has no x's. If that happens, then I can solve it. Or vice versa. If I assume there weren't any x's and it only had y's, if you flip this around and divide it by the n, by the m, you have no x's. And you only have y's. Okay? So let's go back to the problem we were trying to solve and see what we have. The original problem was this thing up here, right? So if we take, let me rewrite the problem so that we have it. Where was my problem? I flipped the page. The original problem was cosine x dx plus 1 plus 2 over y sine x dy equals 0. If I do 0 minus 1 plus 2 over y cosine x, what can I divide by so that one of the variables goes away? That looks like one of the original pieces. I get to divide by either m or n. What can I divide by to make one of the variables go away? Yeah, the cosine x, right? So if I divide this by cosine x, then the cosines go away, right? You agree? Okay. So let's compare it to what we had. Here's kind of our, I know I solved it here, but let's go back up to this piece right here. Okay. We have mu m sub y minus n sub x is equal to mu sub x n minus mu sub y m. What did you divide by, the n or the m? Yeah, the m, right? Because it's divided by the cosine x, right? So I want this piece to go away. That's what we divided by, right? We agree? That was what made the x's go away? Okay. So we're at, if I solve this, you would have mu sub y equals the negative of m sub y minus n sub x over m times mu. Okay? I know it's weird. Pardon me. All right. So this is what we have here, right? This was m sub y. This is n sub x. This is m down here, right? So we're trying to find d mu dy equals, the negatives will cancel and the cosines will cancel. This is 1 plus 2 over y times mu. That's what we're trying to solve. Notice there's a negative in front. The negatives will cancel, right? And then the cosines cancel. Okay. Remember again, this needs to look like e to a power, because the derivative involves the original function. If the derivative involves the original function must have been e to a power, right? The thing that pops out in front has to be the derivative of the power, correct? So the power must be the integral of 1 plus 2 over y dy, which is e to the y minus, plus 2, natural log, holy cow, 2 natural log of y. Should be technically absolute value of y, but the reason I didn't write absolute value of y is I can bring the 2 up and it'll square it. Or even better, I can write this as y squared e to the y. I've got a plus sign in my exponent, so I can write it as multiplication. And then I have e to the log y squared. And then the e and the log cancel. Okay? Phew, that was a lot of work, wasn't it? So you're very excited about that one. That's only our integrating factor. We're not done. Okay? This is the thing that we need to multiply on both sides. Okay? So we have y squared cosine x dx. I'll distribute the y squared through. We'll have y squared. Oh, sorry. I forgot my e to the y, didn't I? Y squared e to the y plus 2y e to the y sine x dy equals 0. That was fun. Now you're ready to solve it. Now, if you're clever, you might already recognize that there's not a lot to do to solve it. Because if you start with y squared e to the y sine x, if you start with that, the derivative with respect to x is this, and the derivative with respect to y is this. If you go through our process for solving exact equations, your function, your derivative of that arbitrary function will be a 0. So you just get a constant in y. So the answer here turns out to be y squared e to the y y squared e to the y sine x equals a constant will be your answer. You can check that actually works. How did I do that? I've done differentiation probably for the last 40 years of my life. No. I'm looking, this has to be the derivative with respect to x, and this has to be the derivative with respect to y. If I just look at this piece right here, the derivative of that is this thing, right? The derivative of this is that thing. So if I just work backward, I needed to differentiate with respect to x to get here, it had to be a sign. If I differentiate with respect to y to get here, it had to be that piece, and it just happens to work. I didn't have to worry about that arbitrary piece that was floating around.
Will it always work like that with these?
No. Oh, yeah. No, because you might still have an extra little piece in there. Most of the way when they're set up that way, it will work, but it may still have a little extra piece on the end. It probably will, because you have to multiply that integrating factor by everything, but I wouldn't guarantee it. I'm sure they can come up with something weird that won't work exactly the right way. I know that was not nice. If I gave you something like this on an exam, I would tell you what the integrating factor is. I would not make you go find it. Because that's two differential equation problems in one. Yeah, wouldn't be the point of the whole problem. So, all right. Anyway, that's integrating factor for that. Are there any questions on that? I want you to let you think about that one a little bit. I put one in the homework. Let you think about it some. The one in the homework won't be on the quiz. Okay. I want you to think about it, see what it looks like. All right, work through it. It's a lot to think about, especially the first time you see it. Okay. All right. I do want to start our substitution methods, which is section 2.5. All right. There are problems that you come across that you can't solve with any of the methods that we've talked about. So, at least in the form that they are in. Okay? So the point of this section is to look at the problem, say, hey, this has a kind of a special form. Can I make a substitution that allows me to see the problem differently to know how to attack it. This is not unnatural to you from other things that you've already done. For example, in Calc 1, you learn U substitution. This doesn't fit one of my antiderivatives that I know, but if I make this substitution, now it looks like something I know how to do. Okay. You do the same thing with integration by parts. This is not a general antiderivative that I know. I'm going to rearrange it into a different form, and hey, now I can do it. Okay? It's the same concept, just in a different context. Literally the same concept. We're going to have two examples of this. Okay? So I'm just going to do it by example. I'm not going to do lots of lecture with it. Okay? I'm just going to show you the two different methods to show you what they look like. Okay? So this is number 4. In section 2.5. We've got y dx equals 2 times x plus y dy. Again, trying our different thoughts. Probably not separable because I've got an x plus y. Those are hard to separate from each other, right? When it's got a plus sign. Not linear because I would have a y times dy dx, right? So not a linear differential equation either, okay? If I do exact, not quite the exact either, because if I take the derivative with respect to y for the dx piece, I get 1. If I take the derivative with respect to x for the dy piece, after moving it to the other side, I get a -2. Okay? I could do that integrating factor. I think in this one you could do the integrating factor thing that we just talked about. Okay? But there is another way to get at it. The way that we're going to use to get at it in these problems is looking at the degree of every single term in the problem, in the polynomial. In this case, it's polynomials. We're going to look at the degree of the variables as they pop up. Okay. What I mean by that is the degree of this one is also as a 1, right? The degree of this term is also a 1. The degree of this term is also a 1. When you've got that situation, you have what's referred to as homogeneous. They go from the definition of the book. You can read the definition of the book. Okay? Not too worried about it. I just like to think about it in terms of look at the degrees of the terms. If they're all the same, we refer to that as homogeneous. Okay? Which kind of makes sense, right? If you think about a mixture being homogeneous, it's all the same, right? So these are all the same in terms of degrees of the terms. All right. If it's homogeneous, then we're going to make a substitution that's going to allow us to rewrite this as a separable differential equation. Okay? The substitution that we're going to make typically is either, well, you could do one of two, but it's usually one. Usually, we'll do u equals y over x, or y equals u times x. And we'll make our substitution. Okay. We'll introduce a new variable and rewrite our equation. Okay? So let's see what happens when we do that. The first pieces are easy. There's only one slight little tricky part. Okay? It's not very tricky. All right? Here we'll plug in u times x for the y. So we get ux dx. I'm not going to plug anything for the x. I'll plug in ux for the y here. Here's the quote-unquote tricky part. I got to plug something in for dy. Y is now a product of two functions, a u and an x. So I have to use a product rule. That's not too bad, though. That's u dx plus x du. That's the substitution. Okay? That doesn't look like it helped us very much, does it? But notice what it did do in the first term here that we didn't have before. I can now factor out an x, and I can separate the x's and the u's. It's multiplication now, right? Okay. So let's actually do that. And I'm going to go ahead and distribute it across the other pieces. Oops, that's a dx. So I factored out the x, and then I distributed over the sum. Okay. So I pulled out the x, and then I distributed that thing through the... Oh, no, I didn't. I forgot a u, didn't I? Sorry about that. Oh, no, I got the never mind. I have it on the end. What are you supposed to do? There, yep. I got one, boo. Come on. Let me have it. Oh my gosh. You're going to have to get better than that. I forgot I put the u on the end instead of below the beginning. All right. Anyway, I pulled out the x and distributed it. I think we're okay here. Okay. All right. Let's see what we've got. Notice if we move this over to the other side now, we can pull out the dx piece, right? I move this over to this side. Pull out the dx piece. I'll write it as ux minus 2x 1 plus u times u dx equals 2x squared 1 plus u du. Looks kind of ugly. That's not horrible. In particular, notice again, I've got an x in both terms, right? So I can pull out the x, and I'll simplify inside a little bit. I've got a u minus 2u, so I'll have a negative u, and then we'll have a minus 2u squared dx. I think I did my arithmetic right. Why did this help? It's separable now, right? We agree? Now a separable differential equation. We can write this as what? We can write it as 1 over x dx equals 2 times 1 plus u over, I'll pull out the negative, u plus 2u squared du. Wish the numbers were a little bit nicer, but it is what it is. Can we solve that now? Yeah, because now I can integrate both sides, right? This one's going to require a little bit of work. You're going to have to use partial fractions. Sorry. Okay. So I'm going to leave that part here. I'll let you do that with partial fractions. Now, if you do want a little bit of extra credit, you can finish this off. Show me the partial fractions. Okay. Then you've got one more piece that you'll have to do at the very, 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 very end. Because notice this is u's and x's. You'll need to substitute back what the u is equal to at the end. Okay. But if you want a little bit of extra credit, go ahead and finish that off. That's okay. Put that on the next quiz. I'm gonna add a couple of points here for the next quiz if you'd like. I'm okay with that. What I do want to do is do one more so we have another example of this. Okay. At least from the substitution part. But you can finish that off. Let's look at number 8. Pardon me. So number 8 has dy dx equals x plus 3y over 3x plus y. Again, we have issues with the techniques that we have before. It's not separable because I got those plus signs, right? That makes it hard. It's not linear. I've got a y in the denominator, right? Probably not exact, but again, I think even if that is not exact, we might be able to do that integrating factor technique we talked about earlier. However, this is homogeneous. Look at each individual term, the degree is 1. Okay. If you've got an x, by the way, for homogeneous, when you're looking for degrees, if you have an x times a y, that's degree 2. Because it would be a 1 times and a 1 together. So you'd add your exponents. So an x times a y is a degree 2 term. Okay. So if you had x squared plus xy, that's homogeneous. Okay. This is the technique that we typically use for homogeneous, by the way, is just to do this substitution and get a separable differential equation. It's not particularly exciting. It's just what we recognize that we can do. Okay. So let's do that. So again, I'm going to write this as dy equals x plus 3y over 3x plus y dx. And we'll let our u equal y at, try that again, y equals ux again. The only reason why I wrote it that way is so that it makes this side a little bit nicer when I do it. dy again is going to become u dx plus x du. I have to use a product rule, right, when I do the differential. It's always going to be that, by the way. On top, do I need to plug anything in for the x? No. X plus 3ux over 3x plus ux. Bless you. And that's it still have a dx on the end. Sorry about that. That okay? That's what it looks like after the substitution. I'll leave my x du on this side and put all the dx's on the other side. But anything nice happen in that fraction? The x's cancel, right? So we've got, pardon me, we've got a 1 plus 3u over a 3 plus u. I subtract the u over. I get x du equals that thing dx, right? Is this now separable? Yeah, it is. I got to flip-flop my u's to the other side and my x's to the other side, but it is separable, right? Okay. So again, at this point, you would separate, integrate, and then substitute back when you're done. Same idea. Okay. This works nicely for homogeneous equations. Okay. So if it's homogeneous, you should be able to do this. Okay. Sometimes they're hidden a little bit as far as what they look like, just to give you what I mean by that. If you look at, this is 13. I may have assigned 13. I don't remember. I'll have to find out in a second. I know we're out of time. I'm just going to do this real fast. Sometimes it's hidden that it's a homogeneous thing. Remember I told you earlier that you might also do u equals y over x? Right? You see the y over x is here? That's why I say it's a little bit hidden sometimes. Okay. This also turns out to be homogeneous, and you can just make literally this substitution. Okay. So again, you would do your y equals ux to be able to do this part easily. But again, up here, you're just going to have a u and a u here. And then it'll turn out to be separable. Okay. Yes?
You said x times y is second degree.
X times y is second degree, correct?
X over y, 0.
No, you would just do the degree at the top and the degree at the bottom. Yeah. Because if you're trying to find homogeneous, you really want it to be the same everywhere. Yeah, so. All right. Let me give you some problems to work on for just this section. There's not many, and we only have done the first half. 2.5, 3, 13. This was 13 that I pulled that out of, by the way. 15 and 21. We'll talk about how to do 15 and 21. Okay. All right. Have a good one. We will see you Thursday or in 15 minutes, whichever the case may be. Don't forget the research presentation again at 2 tomorrow if you're able to come. I know some of you are not able to come for various reasons you've already told me. So, but anyway.